So in this video, I'm going to be doing something a little bit different. I've seen that a lot of people like watching other people studying, so why not study with me? What I'm going to be doing is having a go at some questions from the Isaac Physics GCSE book. Now this is useful for anybody doing IGCSE or GCSE, not just people in England, so people all over the world. And what we're going to be looking at in this session are some questions about force, mass and acceleration. So this is very much Newton's second law, about looking at if you've got a resultant force on an object, what is its resulting acceleration. So the questions could be useful for anybody. In terms of equipment, I've got the book here. Some of you might have seen this at school. You can buy the book for £1 from the Isaac Physics website. But to be honest, even if you don't have the book, you can find all the questions on the website anyways, and I'll show you that in a few minutes' time. Other things I've got a massive stack of paper for all my working out, because I will be writing out the equations, drawing some diagrams to help me get the right answers. I've got a calculator and also a ruler in case I need to draw any diagrams. And especially if we're looking at forces, we're going to be using vector arrows to kind of represent these, and therefore sometimes having a ruler where you can actually measure the length of an arrow is quite important. Apart from that, I've just got my laptop as well, so I can actually type in my answers to check that I'm correct. What I'll do is beneath the video I'll put in some extra details about how to find these questions, how to get to the Isaac Physics website, and also there might be some timestamps on YouTube so you can maybe skip forward to a question if you need to. Don't forget though, I'm only going to be doing one chapter's worth of questions. There's about 60 chapters of questions in here and also extra stuff on the Isaac Physics website. So yeah, study with me. So in this book, the questions I'm going to be doing are to do with resultant force and acceleration. So this is chapter 13. There's actually additional ones as well, which you can just find online. But basically, page 34 is where I'm going to go to. Now, the nice thing about this book, and especially having it in front of you, it just shows you how many questions there are that you can have a go at. And you don't have to wait for your teachers to set this as a homework or a class task. This is something that you could work through independently if you've got that motivation. It starts with a bit of the kind of physics behind it. So this is stuff that you can read. It's got a worked example as well, showing you maybe a simple diagram and actually how to calculate the answer. So we're going to be starting from question 13.1. We're going to have a look at these questions over here. There's another example here, and then we look at actually how we calculate the acceleration. So this is the work we're going to be doing. Now, if you don't have the book, or in order to actually check you've got the right answer, what we need to do is have a look at the Isaac Physics website. So if you just type in Isaac Physics, you should be able to find the website pretty easily. So there's loads of stuff here that you can have a look around at some point. We're going to look on the main page where it says GCSE. So if you click on this, it has various different things here. So it's got some quick quizzes that are quite good that you can have a go at, a bit about how to actually solve problems. There are some mentoring schemes that they have, so I'll let you have a look at that. But we're looking at the Physics Skills Mastery. So this refers to the book that we're looking at the moment. You can obviously buy the book here. There's more stuff for teachers. But actually, when it comes to us answering the questions, we're looking at chapter 13 about forces. That's in mechanics. So if I click on this, we can then see resultant force and acceleration. And if I click view board, this then brings up the board which has the questions, okay? Again, within this, it's got, if you click on this orange one here saying resultant force, that's very much the notes which are in the book. It's got the worked example. It kind of shows you how to answer that. So there's a lot here that you can have a look at. But we're going to be wanting to start with question 13.1. So you can see here, the question that is online is the same as the one that's in the book. And when it comes to writing in your answer, what you need to do is just type in your value here. So that's your number, and then choose the units. So this is how we're going to be actually entering our answers. Okay, so 13.1, for these questions refer to the diagrams, so the ones over here. Work out the strength and direction of the resultant force for each object. You could always draw the vectors nose to tail, and then maybe think about Pythagoras if there's something with things at different directions. Work out the strength and direction of the extra force which would need to be added to achieve equilibrium, so no resultant force. Okay, so the first one, hopefully you can see that. the first one, so I'm just going to put, so this is my working out, so 13.1, part 1, we've got an object here, so I'm just going to draw that as a dot. I'm just going to do a sketch diagram, so I've got 3 newtons this way, 3 newtons that way. If we think about what happens if you've got 3 newtons this way and 3 newtons that way, if you add the vector arrows nose to tail, they come back to where they started. You know, and that means that there's balanced forces, and that means in this case the resultant force is going to be equal to 3 minus 3, which is just equal to 0 newtons. Okay, I'm going to go and put these onto the computer in a couple of minutes' time to check. The second one, so we've got an object of 3 kilograms, you've got 6 newtons to the left, 12 newtons to the right, so my resultant force would be 12 minus 9, and that's equal to 3 newtons to the right. Okay, this time I didn't draw a diagram because I thought it was quite simple. Number 3, we've got 50 newtons left, 20 newtons right. So we're going to say 20 newtons, take away 15 newtons, means that there's a resultant of 5 newtons to the right. And I'm just putting my arrow in there to remind me. Number 4, this is more tricky. So we've got 3 newtons left and 3 newtons right, so they cancel out to make 0. And that means then there's a resultant force of 2 newtons down. So effectively that and that cancel each other out. So there's no resultant force left and right, but there is a 2 newton force down. I'm just going to put that as 2 newtons down. Number 5. So we've got 12 newtons to the right, 11 newtons and 9 newtons, okay? So I'm going to say, and think about forces to the left, you've got 9 newtons to the left, plus another 11 newtons to the left, and take away 12 newtons to the right. So 9 plus 11 is 20, take away 12 is equal to 8 newtons. And this is going to be to the left. Now another way I could have approached that was I could maybe think about adding the arrows up. So we might say, maybe we had an arrow which was 9 along, we had another arrow which was 11, and then we have a force to the right of 12. And that means that the resultant force, which is kind of effectively this size here, I'm going to put a double-headed arrow to show that's resultant, is going to be equal to 9 plus 11, take away 12, which is 8 to the left. Hopefully that makes sense. It kind of makes sense, I guess, because I've done a lot of these questions before. And then finally, number 6, we've got a force of 3 newtons to the right. We've got a force of 4 newtons down. Okay. Now, what we have now are forces at right angles to each other, and effectively it's going to be slightly to the right and down, and the resultant force is going to be like this. Okay, so it's kind of that much long and that much down. We can always think about this in terms of maybe adding the arrows end to end. So we've got 4 newtons down, we've got 3 newtons to the right, and that means the resultant is going to be from the start to the end of the arrows, which again is this line down here. Now, this kind of makes it probably a bit easier to see. We've got a right angle triangle, and because we've got a right angle triangle, we can use Pythagoras. So if we want to find out the side, let's just call this A. We know that A squared equals B squared plus C squared. So the length of this side, A, is going to be equal to this squared, so that's 4 squared, plus 3 squared, and then we want to square root that. 4 squared is 16, 3 squared is 9, so 16 plus 9 is 25. So A is going to be equal to the square root of 25, which is just 5 newtons. Okay, and in terms of this part here, the direction we can put left or right, we'll just leave that at the moment and see if we actually have to put the direction as an angle in this question over here. So I'm now going to input my answer. So this is why I wrote it on a piece of paper. I can have my scribbles here, and that really makes it easier when it comes to looking at putting my answers onto the Isaac Physics website. So for part A, I said that the answer was equal to 0. The answer is going to be given in newtons because we're looking at a force. Check my answer, correct. Oh Christ, there's a lot. Look at this. Okay, so the next one, the value for part 2, I had 3 newtons, and my answer, oh, hold on, is it 3.0? Oh, here we go. Okay, this is what I've done. So part A was basically working out the size of the resultant force. Part B, which is what I'm answering at the moment, is looking at the force that would be needed to achieve equilibrium. So if it's already in equilibrium, there's no force needed to get it into equilibrium. And for part C, so part C here is now for question 2. I see. So basically, I think what I need to do is I didn't read the question properly. So part A is for question 1, part B is for question 1, part C is for question 2, part D is for question 2, and so on. So what's the resultant force in this example here? This is going to be equal to 3 newtons. And if I check my answer, that's correct. What's the force needed to keep it in equilibrium? That's also going to be equal to 3 newtons. Check my answer. Okay. If we've got 3 newtons, which we're thinking of as positive, then we need to have a force of minus 3 newtons, because force is a vector quantity. So if we're saying that the resultant force is 3, we need to have we need to add a force of minus 3, so that'd be an extra 3 newtons to the left to keep it in equilibrium. Okay, I'm a physics teacher, and I've just kind of sort of rushed ahead. So the next part is for question 3. So the resultant force on the object is 5 newtons. And that means that the force for equilibrium to keep it there would be 5 newtons in the other direction, and so on. So I think basically for all of these, we're going to have whatever our number is and then the negative value of that number. Okay, so part G, so this one here is where the 2 forces balanced either side. We're going to have a resultant force of 2 newtons down. I suppose I probably really should be putting 2.0 newtons, so the same amount of significant figures as this, but Isaac Physics, let's have a look. Okay, this is why. So forces up or to the right are defined as positive. So if the force is down, then that means the resultant force in this scale, because we're saying upwards is positive, so if the resultant force is down, it's going to be a negative value. So that's negative 2. So to make the force in equilibrium, we need to add another plus 2 newtons upwards, which is correct. This one here, so we're saying that the resultant, so forces to the right are positive, so forces to the left are negative, and that means that if we've got a force of 8 newtons to the left, which is what I wrote down, we'd have the resultant force being equal to minus 8 newtons. And to make it in equilibrium, we'd have to add another 8 Newton force to the right. Correct. Okay, it's going to fill in the last few. This one is a bit more difficult. So the strength of the resultant force. Okay, so this is the size of it. We worked it out as 5.0 newtons. So I'm just going to put in 5 there. Check my answer. Correct. What's the resultant direction? So now, for this one here, we need to work out the direction of the resultant force on the object, define the horizontal axis as the origin of the angle, and turn clockwise as positive. Give the answer in degrees to 2 significant figures. So this is quite tricky. It's not an easy thing. So let's have a look at the best way we can actually work that out. So effectively what we want to be doing is working out this angle here, theta. So we're saying that this direction along here is kind of where we have 0 degrees, and then going clockwise is where we measure our angle. Okay, so let me just draw this triangle out again, just so it's even bigger. Okay, so you know that this side is 4, we know that that side is equal to 3.0, and this side is equal to 5.0. And we want to work out the value of theta here. Okay. Now we can do that by working out this angle in here. I'm going to call that angle alpha. Because if we know this angle here, we just take the angle alpha away from 90 degrees to get our angle of theta. And we can do this by using some trigonometry. So this is using sine, cos, and tan. Now on this triangle, if this is the angle that we want to find out about, we've got other sides. We've got the opposite side over here. Actually, I'm just going to move to another colour. Okay, so this is the angle we want to find out. This side here is opposite to that, so I'm going to put an O for opposite. This length here is the adjacent side, and the longest one is a hypotenuse. And what we want to look at is the angle here. Now, we could use sine, cos, or tan, remembering, of course, that SO8, so remembering SOHCAHTOA, we could use, because we know the opposite hypotenuse and the adjacent, we could use any of these. I'm going to use tan, and what we can say is that tan alpha, because I've called that angle alpha, is equal to the opposite side over the adjacent side. And that means our angle alpha is going to be the inverse tan of opposite over adjacent, so that's 3 over 4. Okay. Now you might have done this in mathematics. If not, you can always just leave the question. So the thing I'm going to check up here is that the calculator, you can just about see that is in degrees mode. That's really important. And then we're just going to do shift tan to make it inverse tan. The brackets come up on this calculator. 3 divided by 4 is just 3/4. So 0.75. This gives an answer of 36.86. Okay, now that looks about right. This angle here looks to be about less than 40 degrees. If it was more than 45 degrees, this line would be coming out like this. So what I'm going to do is take this angle away from 90, so 90 minus my answer, to give an angle of 53.13 degrees. Okay, so when it comes to actually inputting my answer, I think probably an answer of 53 degrees to 2 significant figures, just like my raw data, should be appropriate. Okay, so we said the angle was 53 degrees. Yeah, and it says up here to answer to 2 significant figures. Because it's an angle, there's a degrees sign there. Check my answer, correct, phew. It's always nice when you get a harder one correct. Okay, so for this one here, work out the strength of the extra force which would be needed to be added in order to achieve equilibrium. Well, before we said it was 5 newtons, so if I put in 5, so it's the same size force, what would the direction be? So work out the direction of the extra force which would needed to be added to find the positive horizontal axis as 0, and this is going to be the positive number. Now before, we had an angle down here which we said was equal to 53 degrees, but we want the direction now to be going from the bottom left to the top right. And so to get this direction, effectively what we need to do is add 180 degrees onto our previous answer. So 53 add 180 is 233 degrees. I just worked that out in my head. I think you could be able to do the same. And it does say here, give the answer in degrees to 3 significant figures, which is what we have over here. So if I check my answer, correct. Okay, and comparing answers. Compare the resultant force to the force needed to achieve equilibrium for each question. What do you notice? They are equal in magnitude and opposite in direction. They're not equal, because if they were equal they'd have the same direction. The force needed is the reciprocal. The reciprocal basically means 1 divided by, so it can't be that one either. That would mean that they're inversely proportional. This one means that they're directly proportional, but just in opposite directions. And to check my answer, I'm correct. So now we've done that, we can go back to the board, and you can see I've completed this. Now, if you want to save your progress, what you can do is you can log in and create an account. If you click log in, you just have to enter your email address. It's all really straightforward. I'm sure you can log into a site like this. If you can make TikTok accounts and everything, that you'd have no drama with this. But that means you can actually record what you've done. So we've now done the first question from this page. Okay, I'm just going to put that to one side and we'll have a look at the next question. So 13.2, calculate the acceleration of each of the objects in this one here. Right, so it looks like a small question, but actually for each of the examples that we saw on the previous page, if we know the resultant force and we know their mass, we can work out the acceleration. So the way I'm going to be doing this is, I might use the same bit of paper. It might start to look a little bit messy. What I might do is go to green to show that this is my new working out. So for question 13.2, we want to know the acceleration. Now we know that there's an equation that says the force equals mass times acceleration. And to work out the acceleration, this is going to be equal to the force divided by the mass. Okay, so that's the equation we're going to be using. So actually, I might write it on another bit of paper. So this will just help me. The thing is, I've got loads of paper. It's all going to get recycled at the end. So for each of these equations, we're going to say the acceleration is equal to the force divided by the mass. Now, for the first part, last time, what we had was that the resultant force is equal to 0 newtons, and we don't need to worry about the mass because 0 divided by anything is still going to be equal to 0. So for the first one, the acceleration is going to be equal to 0 divided by whatever, and that means the acceleration is going to be equal to 0 meters per second squared. Okay. The second one, we worked out that the resultant force was 3 newtons to the right, and because it said that to the right was positive, we can say that this is plus 3 newtons. The size of the mass for that second one was 3 newtons. So the mass was equal to 3.0 kilograms. Acceleration is force divided by mass, so that's 3 divided by 3, which is just equal to 1.0 meters per second squared. And because acceleration is a vector quantity, it has direction as well as magnitude, that's going to be a value of plus 1.0 meters per second squared, which is going to the right. Okay. The third one, the force was equal to 5 newtons to the right, so that's plus 5 newtons. The mass was equal to 10 kilograms, it says here. And again, all I'm doing here to kind of, especially when you get a little bit more complicated, I'm just writing down the data that we know. So F equals 5 newtons, M equals 10 kilograms. Acceleration, force divided by mass, put in the equation, doesn't take long to do. Force was plus 5, mass was 10, and that's just 5 over 10 is just a half. So it's plus 0.5 meters per second squared. Okay, writing out the raw data, the equation, working out answer unit. Do that every time. You cannot make a mistake, or it's very unlikely that you make a mistake. Okay, the fourth one. So this was where I had 2 newtons down, and we're saying that downwards is negative from the way that IGCSE Physics decided which is positive and which is negative. So the force is minus 2, and I suppose it's really minus 2.0 newtons. The mass was equal to 5.0 kilograms. Acceleration is force over mass, so minus 2 over 5. So 2/5 is equal to 0.40. And I'm going to say this is minus 0.40 meters per second squared. Okay, because that's going in the downwards direction. For number 5, we had a resultant force equal to 8 newtons, so that's minus 8.0 newtons. The mass was equal to 20 kilograms. Acceleration, force over mass, so minus 8 over 20. Minus 8 over 20 is the same as minus 4 over 10. So again, it's the same answer, minus 0.40 meters per second squared. This time it's going to be going to the left. And finally, our last one, for number 6, the size of that force was equal to 5.0 newtons. the mass of the object was 20 kilograms, and that means the acceleration is going to be equal to 5 divided by 20, so it's a quarter, so 0.25 meters per second squared. And the direction of that, I think we said last time, by working out, and this is tricky using this stuff, using trigonometry, the direction was equal to 53 degrees. Okay, so that's my raw data. I'm now going to start inputting that again onto Isaac Physics to see if I've got the right answer. Okay, so 13.2, part A, so we've got calculate the acceleration of the object. So here the acceleration is going to be equal to 0, and the units are meters per second squared. Oh, meters per second squared, check my answer, correct. Part B, we said it was +1, so 1.0, units are meters per second squared, that's correct. The next one, 0.5, units are meters per second squared, and this really makes you start to know your units. Okay, 3 forces. Because it's going down, it's going to be a negative number, and we said negative 0.40 meters per second squared because it's an acceleration. That's correct. The next one, I think it's the same answer, and it was minus 0.40 meters per second squared. Check the answer. And 2 forces. So it says calculate the magnitude, so that's just the size, so you'd have to put in the angle. And this was 0.25, I think, meters per second squared. Correct. Back to the board. It's actually quite satisfying when you start to get these all correct. So the next one we're going to be looking at is 13.3. So a table where we need to work out some missing values. So I think I've kind of finished with this paperwork. All I'm going to do is just put it to one side. I mean, I might need it later, but I'm pretty sure I'm done with that. So the next question is using this table here. Now, this is my book. I mean, it's not really my book. I think it was given to a student who I then stole it from at one of the schools I worked with, but it's only £1, and I think it's £1 well worth spent if you can actually write in your book. So sometimes, yes, it's absolutely vital that you kind of, like you need to draw diagrams, you can work on paper, but I think, it's like a workbook. It's not something that is going to be kind of kept for many years on your bookshelf. So I don't see any issue with writing it, but it maybe depends on what your school say. It might be that you just write in pencil and rub it out afterwards. I would take the hit, I'd write in the book and then give the teacher £1 at the end of it. So I'm just going to write my answers in for this. Each row represents a different question. So for this row here, we want to find the resultant force, and we know the mass and the acceleration. So to the side, we can say that force equals mass times acceleration. The mass here, so we just need to multiply these two numbers together. So that's just 810 multiplied by 6.7. What I'm going to do is write in my full answer of 5427 newtons. Okay, now I suppose I could round this down to 2 significant figures, like my acceleration. So I could always give my answer as 5,400, I think. But I'm just going to leave my raw data here in the table. Same for the next one. Resultant force is just mass times acceleration. This time it's 43000 multiplied by 2.6. Again, big numbers, 1118000. I was going to put in a comma there to show that that's 1,118,000. To work out the acceleration, acceleration is the force divided by the mass. So that's just rearranging this equation here. So the force is 2,000 divided by 65 to give 30.769. So I'm just going to put that as 30.77. So I've just given it to a few more significant figures than I need, but maybe I can round it up to 31. And finally, the force here is the mass times acceleration, but here they've given the mass in grams. So to convert from grams into kilograms, what I'm going to be doing is dividing by 1,000. Okay, so 10 grams divided by 1,000 is 0.01 of a kilogram. Okay, we can now use this value here, because this is now our mass, times it by 9.8, which you might see as the acceleration often due to gravity, to give a resultant force of 0.098. So, a bit messy, I understand it, and what I'm going to do now is just put this again into IGCSE Physics into the table. Okay, so part A, the resultant force, the value, please answer to an appropriate number of significant figures. So really the answer should be given to two significant figures like that, and my answer was 5427, so I'm going to put 5400. A force, so it must be in newtons, check my answer, and there we go, that is correct. The second resultant force, again, to an appropriate number of significant figures, well, my answer was at 1,118,000, so I'm going to put 1 million, and then this is my, I'm basically rounding it down to the nearest 100,000. And you can see why we use standard form for long numbers in physics, because otherwise you get too many zeros. That's correct. The acceleration here, two significant figures here, so two significant figures should be appropriate. I worked it out as 30.77, so that's 31 to two significant figures. It's an acceleration, so it's meters per second squared, and that's good. And then finally the resultant force, we had a 10 gram mass, and this was a value of 0.098, so 0.098. That's still to two significant figures here, the 9, 8 are significant. The units are newtons, and that's correct. So back to the board. Okay, so moving on to question 13.4. So a 100 gram mass has a weight of 1.00 newtons. If this is the only force on the mass, what is its acceleration? So this was quite difficult because it's just words, there's no diagram. So the first thing that I'm going to do is just draw a diagram to represent that. So this is my 100 gram mass. So m is equal to 0.100 kilograms. So this is just my mass here. It has a weight of 1.0 newtons. So this is my force down. So I'm going to say then that the weight is equal to 1.00 newtons. And this weight, if this is the only force on the mass, what is its acceleration? So F equals ma. The acceleration is going to be the force divided by the mass. Here the force on this object is provided by the weight, so that's equal to 1.00 newtons. The mass is 0.100, and then we've got 1 divided by 0.1, which is the same as 10 over 1. So the acceleration would be equal to 10. And in this, because it's an acceleration, would be given as meters per second squared, and that's acting down. So a 100 gram mass with just its weight acting on it would accelerate at 10 meters per second squared. Okay, what would be the weight of a 300 gram mass in the same gravitational field? So for part B, you've got to remember that weight is equal to mass times the gravitational field strength. So the weight would be the mass, which is 300 grams, so 0.300 kilograms, multiplied by g. Now, g, if you're doing A level, is equal to, we often use the value of 9.81 meters per second squared. G for some boards at GCSE, you use a value of 9.8. When I say meters per second squared, it's also newtons per kilogram. They're both the same unit, really. So often at GCSE we use 9.8 newtons per kilogram, or sometimes at GCSE we use 10 newtons per kilogram. So I'm going to use this value for G at the moment. So I'm just going to multiply this by 10. I think actually in the IGCSE Physics book, it does have some data at the front. So over here, gravitational field strength, G, is meters per second squared or newtons per kilogram. Does it give a value to use? It doesn't really give a value to use, but I'm just going to use the value of 10. So 0.300 times 10, so 0.3 times 10 is equal to 3.00 newtons. Okay, so if you've got three masses, 3 times 100, as we had before, that's 300 grams, so 3.00 newtons. Okay, if the weight is the only force on the 300 gram mass, what is its acceleration? So for part C, I'm going to draw a diagram again. So this is my 300 gram mass. I've just drawn it maybe bigger than the one over here. So the mass is 0.300 kilograms. The weight acting on it, the resultant force, I'm going to do a bigger arrow than before to show that this is a bigger force. Hopefully you can see that. So the weight is 3.00 newtons. F equals ma. Acceleration is force divided by mass, which in this case is 3 newtons. So that's the resultant force divided by the mass of 0.300. 3 divided by 0.3 is the same as 30 over 3, which is 10 meters per second squared. So what we find is that if you've got something which is heavier, okay, it's got more mass, but it's got a bigger force in it. So if you were to drop 3 newtons, or you dropped 1 newton, even though this is bigger, they both accelerate at the same rate in that gravitational field, providing obviously there's no big effects due to air resistance. So I've got my answers. I'm just going to check. I hope I'm correct, but I'm just going to put them onto Isaac Physics again. Okay, so the first one we said the value was 10 meters per second squared. 300 gram mass has a value of 3.00. So that's 3 significant figures. An appropriate answer would have 3 significant figures. It's a weight, so the answer would be newtons. And the acceleration of 300 gram mass, a common misconception that lots of people have is that heavier things fall quicker. Heavier things and light things fall at the same rate, provided there's no air resistance. There we go, back to the board. You can see now it's starting to look a lot more complete, which is really nice. Okay, next one is 13.5. So for question 13.5, I'm just going to work in the book because I can't be bothered to write out a whole table. Complete the table. So it's the table up here. Each row is a different object. One forwards, one backwards. Define forces accelerating as forwards is positive. So is it going to be speeding up or slowing down? Okay, so yes, we're talking about a static object. It then has these forces acting on it. So the first one, the resultant force, we're going to say that forwards is positive. So I'm going to put a positive thing here. Backwards is negative. So just to remind myself, I've got this. So the first one, if it's going forwards with 58, we take away 16. So 58 take away 16, I can do in my head, but it is equal to 42. That's my lucky number, the number on my motorbike. So the resultant force is 42, and it's going to be forward, so I'm just going to put a positive thing there. We can then work out the acceleration. We know that force equals mass times acceleration. So the acceleration is equal to the force divided by the mass. Even though I've done this many times before, just write it down. It just means you're so much less likely to make a mistake. So for this one here then, the acceleration is going to be equal to that force divided by that mass. So I'm just going to put that being equal. I probably should have drawn this on a bit of paper rather than just in the book. But that's going to be equal to 42 divided by 5.6. So 42 divided by 5.6 is equal to 7.5 meters per second. And that means it's speeding up because it's got a positive value of acceleration. Okay, the next one, so that's A, that's B, C. Again, we've got plus 90, take away 145, so that's 90. Forwards, take away 145 to the left, going backwards, which means the resultant force is minus 55 newtons. So it's going to be a backwards force of 55 newtons. I'm going to keep the same thing here. We want to work out the acceleration, which is the force divided by the mass. So the force is minus 55 divided by the mass of 22 kilograms, divided by 22, gives an answer of minus 2.5 meters per second squared. So this one here, it would be either accelerating to the left, or if something was moving, it would then be slowing down. Okay, the next one, we don't know we only know one force. We don't know the resultant. We know so basically, in order to work out the resultant force, we can use our mass and acceleration. So the mass times acceleration is the resultant force. So that's going to be equal to 120 kilograms times 6.7. So the resultant, that's 120 multiplied by 6.7. So the resultant of these two things is 804. And that's going to be a positive value because we had a positive acceleration. So something, take away 350 is 804. So I'm going to add on 350 to this to find that my forwards force is 1154. So to be honest, I probably should have done this with a bit of paper. It's getting a bit cramped on this, but I think I've got enough there. So again, just going to check my answers on IGCSE Physics. Okay, so you can see there's a table here again. Something else I probably haven't mentioned yet are the fact that on IGCSE Physics there are hints as well. So hint 1 basically takes you to the page of notes about the kind of the basic physics. So if you're not sure about an answer, if you're not sure how to approach a question, have a look at hint tab 1, and it brings up some notes for you to just remind yourselves of that basic physics. What's more exciting is hint 2. And there are videos. In actual fact, there are 2 videos for this chapter, and I am speaking. So what I did was I made some videos that IGCSE Physics have. Hopefully you can hear the sound just about. So for every chapter, there's 1 or 2 videos, and basically what I do... Force of 6 newtons acting to the left. It's my voice. But what would happen if we had made... What we can now do is... So basically what I did in these videos was I went through the physics theory. I then, later on in the video, I did a worked example in the style of IGCSE Physics. Actually, that's probably the same pen I'm using today in this video. So if you're not sure and you want to find out a bit more, there are lots of videos on IGCSE Physics that kind of go through everything for the GCSE book. Okay, so that's another one of the hints. Okay, so if we go to answer now. So for the first part, part A, we said the value was plus 42. It's a force in newtons. Check my answer, it's correct. The acceleration with that value we calculated as plus 7.5. Oh, hold on. Oh yeah, it's not newtons, is it? It's an acceleration, so it must be meters per second squared. Honestly, if you do these questions, you'll get so good at putting any of the right answers in. For part C, so the resultant force on the 22 kilogram object, so the resultant force acting on it is minus 55 newtons. Its acceleration, what's the acceleration of this one here? That was, we calculated, because it's got a negative resultant force, it's going to be a negative acceleration of minus 2.5 meters per second squared. For part E, the value that we had for the forwards force was, we eventually calculated as 1154 newtons. Oh, so okay, so 2 significant figures, and I gave mine to 4. So to give that to 2 significant figures, I'd round it up to 1200, which is good. And actually, it kind of basically lets me know there that I've got the right answer, but I haven't expressed it correctly. That means the resultant force is 804. I should give that to 2 significant figures, which is basically 80. There's another 0 there. So the units for that are newtons. Correct. Now the first row. Is the object speeding up or slowing down? I reckon because it's got a positive value of acceleration, it's going to be speeding up. Correct. Second row. is the object in the second row speeding up or slowing down? So it's got a negative value, so I'm going to say that this one is slowing down. And that's provided you've got a moving object which experiences these forces. In the third row, you've got a positive value, so I'm going to say it's speeding up. And there we go, back to the board. Okay, so based with this knowledge here, we're now going to go a few more questions. So the next one, 13.6. What is the unbalanced force that acts on a 70 kilogram mass if it accelerates at 1.6 meters per second squared? So I'm just going to draw a diagram. So this is my mass, and I know it's 70 kilograms because I've just said that. It's got a force acting on it, and we don't know the size of that force, but we know that it accelerates at 1.6 meters per second squared. So this one here, simply force equals mass times acceleration. So the force is equal to 70 kilograms times 1.6 meters per second squared. And if we do that, 70 times 1.6 is just equal to 112 newtons. So there we go. Let's just check that's correct. So 112 to an appropriate number of significant figures would be rounded to 110 units in newtons. Check my answer. Correct. And there we go, that was it. Sometimes I think people assume that the later questions are going to be harder than the first ones. I think personally I found so far that the hardest question has been this one here where you need to work out the direction. So that's using trigonometry. That's a difficult skill that you might only really get to grips with by the end of year 11. This one here was quite an easy question. Okay, let's go to 13.7. What is the acceleration of a 10 kilogram mass which has no unbalanced forces acting on it? So, okay, that's a difficult thing to understand. So this is my mass. So my mass is 10 kilograms. It has no unbalanced forces acting on it. So it's like a double negative. So that means there are balanced forces acting on it. So the resultant force is equal to 0. So the acceleration is equal to 0 meters per second squared as well. So the answer is 0 meters per second squared. Right, so that was a really easy calculation because it basically means if there's no unbalanced forces, there are balanced forces acting on it. If there's balanced forces, there's no resultant force and therefore no acceleration. But we're correct. Okay, so let's move on to 13.8. So for 13.8, we've got, I'm just going to underline this stuff, so we've got a 1200 kilogram vehicle. And that's about the mass of a normal kind of car, so maybe a small car is about 1.2 tons, 1200 kilograms. It's accelerating on a straight road at 3 meters per second squared. What's the magnitude of the force acting on it? So this is my car. Okay, we know that the car has a mass equal to 1200 kilograms. There's a certain force. This is a resultant force acting on it. And we know the acceleration at this point is 3.0 meters per second squared. F equals ma. You can do this in our heads. So the force is going to be equal to 1200 times 3.0, which equals 3,600 newtons. Correct. Actually, these later questions, I guess they seem straightforward, but that's because of all the work that we've done before this. So the next question, 13.9. So let's think about, first of all, this is the object. It's got a mass equal to 3.0 kilograms, like it says over here. What force must I apply to accelerate it to 4 meters per second? So this is the force being applied, F, and we want to accelerate it at a value of 4.0 meters per second squared. Now the first one says there's no friction, and that means in the opposite direction to the direction the force is being applied in its motion, the friction, also F, is equal to 0. So in this case here, the resultant force is just equal to its mass times acceleration, which is 3.0 times 4.0, which is equal to 12 newtons. Okay, that's all pretty straightforward. For the second part, so this one here is part A. For part B, I'm going to draw that there's a frictional force of 4.0 newtons acting in the opposite direction to its motion. So that means there must be a bigger force needed to accelerate it. And again, the acceleration, we still want it to be at 4.0 meters per second squared. The mass is still 3.0 kilograms. Okay, and we want the acceleration to be equal to the same value. So that means the resultant force on the object still has to be this value here. So the resultant force equals 12 newtons, and that's going to be going to the right. But now we've also got to overcome this 4 Newton here. So in addition to this 12 newtons, we have to add on another 4 newtons to kind of overcome that. And that means that the resultant force, so the force over here, F, is going to be equal to 12 plus 4, which is 16 newtons. So here we need to apply 16 newtons rather than the 12 newtons to keep it going at the same acceleration. So let's just check that again. So 13.9, the value, if there's no friction, would be 12 newtons. And if there's a frictional force of 4 newtons, then the force we need to apply increases by 4 to 16 newtons. Correct. Back to board. One more question to go, 13.10. Now the thing is, it's actually really nice, if I just go back to the board, that basically when you get all of these correct, that means that you've basically mastered this skill. And that means you've got a great deal of knowledge, which means you can approach any problem like this in the future. Because you know, if you've done this many questions, you know that F equals ma, and you can actually work out the resultant force, calculate the acceleration. So let's have a look at 13.10. So I'm going to treat myself to another bit of new paper for 13.10. Now, first of all, there is a lot of data here. And this is why it's difficult, because there's a big long sentence. You've got to work out what's relevant and what isn't. Also, I've got my Lego space shuttle, because it's been far too long without any Lego, and I think, this is the perfect size to illustrate this question. So, a rocket engine. So it might be some of these rocket engines here that were kind of basically blasting off into space. It's equal to the mass of the propellant burnt by the exhaust velocity. Okay. So I'm just going to write some data down. So the space shuttle, with its booster rockets and its external tanks here, had a total mass. So the total mass was equal to 2,040,000 kilograms. Okay, so that's its mass to begin with. The exhaust velocity of the gases was 3,000 meters per second. I didn't know that. That seems pretty quick. How much propellant would have to be burnt each second in order for the spacecraft to just lift off? So when it's just about taking off, how much propellant would have to be burnt each second? So it says here that the thrust generated by a rocket is equal to the mass of the propellant burnt each second multiplied by the exhaust velocity of the gas. So the thrust is equal to the mass of the gas multiplied by the exhaust velocity, which is up here. Okay, what do we know so far? There's a lot of stuff here. Well, we know that... okay, let's think about this. So we've got the space shuttle here. It's got a certain thrust that has to be acting upwards for it to take off. So this is its thrust. Now, when it's just about taking off, there's a downwards force equal to the weight. And if the thrust and the weight are equal, it's not really going to be doing anything. Basically, the thrust has to be just about bigger than the weight for it to just about take off. Okay, and so what we can then say is that the thrust must be equal to the weight, and at that point, if the thrust is maybe just 1 Newton bigger than this, it would then start accelerating upwards. So for it just to take off, the thrust is equal to the weight. Now the weight of that rocket is going to be equal to mass times the gravitational field strength. So the weight of this rocket was our 2,040,000 kilograms multiplied by 10. I'm going to use 10 as the gravitational field strength. So I don't need to work that out. So the weight is equal to 2,400,000 newtons, which is also then equal to the size of the thrust. Okay, and the thrust here is equal to the mass of gas times the velocity. So 20,400,000 newtons is equal to the mass of gas burnt each second multiplied by their velocity, which it says here is 3,000. So the mass of gas burnt each second is going to be this value divided by 3,000. So that's 20,400,000 divided by 3,000. So each second, 6,800 kilograms of gas is, I say gas, of propellant is burnt. So let me just check this, because it's worth checking before we go into part B. So propellant, I said 6,800 kilograms per second. Correct. That's good. This is a multi-step calculation and there's a lot of data, so I'm pretty pleased I got that first attempt. Okay, the second part looks at how much propellant would need to be burnt each second in order for the spacecraft to accelerate upwards from the launch pad at 3G. Okay, so the reason we're thinking about when it's accelerating at the very beginning is because that's when we know the mass of this. Obviously, as time goes on, as it gets higher and higher, it will have burnt off more mass, and that means its weight will be less. Okay, so we're thinking about at the start when we know its weight. Okay, so what I'm going to do is on a different piece of paper, I'm going to draw the thing here where we know the weight of the object here. We want to calculate the thrust, which I'm going to call T, and basically the resultant force F must cause there to be an acceleration of 30 meters per second squared. So if we know the size of the resultant force causing this acceleration, we can then work, and we know the weight, we can then work out the size of the thrust needed to accelerate at 30 meters per second squared, or 3g, and we can then use that to work out the mass. So to work out the force is equal to the mass times acceleration. Now the mass of that rocket is 2,040,000 kilograms times by this value of acceleration of 30. So the resultant force has to be, it's going to be pretty big, so it's 20, 40, 6, 1, 2, there's 5 zeros, aren't there? This is why standard form is quite useful, but I'm just going to keep it at 61,200,000 newtons. Now, in order to have this as a resultant force, the thrust must be even bigger than this because there's also the weight. And effectively, the thrust is equal to the size of the resultant force plus the weight, or I guess taking away the weight, which is acting in the direction. So here, the total thrust must be equal to 61,200,000 newtons plus the size of the weight, which is 20 million newtons. So 20,400,000 newtons. So the thrust must be these two numbers added together. So that's going to be equal to 81,600,000 newtons. Now again, we know that the thrust is going to be equal to the mass of propellant burnt off multiplied by the velocity of that gas. So that means the mass of propellant burnt each second is going to be 81,600,000 newtons divided by 3,000. So I'm just going to, on my calculator, add this number to 2040. Which then gives a mass burnt each second equal to 27,200 kilograms. So let's just check that I'm correct. So an appropriate number of significant figures would be 2 for this. I'm just going to say 27,000 kilograms per second is correct. It says I might have used G as 10 rather than 9.8 in the first one. I don't know if I did use that, but anyway, it doesn't really matter which value you use. I think Isaac Physics records that. So back to the board, look at that. So that was my approach to having a go at the questions. It probably took me a lot longer because I was explaining it and I was kind of writing out my stuff. But you can see that even though I know what I'm doing as a teacher, I still had to really spend my time thinking about this question. This is my working out. But because I kind of spent the time putting the equations, thinking through it, drawing diagrams, that allowed me to get to the correct answers. So that's just the questions on force and acceleration. I know that there's more that you can do online. And then I guess moving on, there's other stuff here about terminal velocity. There's loads of stuff. Basically, if you want to kind of get the higher grades or just understand physics better, I reckon it's really worth having a look at this book. If you've watched the whole video, that is incredible. If you've done this as well, please leave a comment beneath the video letting me know that you've actually done this, you've found this useful. But hopefully that just gives you a bit of confidence that you can approach this book here or questions like this if you spend enough time just following the basics, drawing out diagrams, putting down your equations, identifying the right bit of stuff in the question, and then giving your final answer to an appropriate number of significant figures with the units. If you keep doing that, keep those skills practiced, you'll have absolutely no problem with GCSE, A-level, or whatever it might be you're doing in the future. But thank you for watching. Appreciate your time. Thanks.